As the last application of Ampere's law to problems with cylindrical symmetry, I'm going to solve the coaxial cable problem. So this picture shows a coaxial cable. These kind of cables are used frequently for sending radio frequency signals. In the old times, of course, the communication between computers were actually mostly carried out with these kind of cables. The reason why they choose this kind of a design is that somehow with this design the coupling with the outside is minimized, so therefore their actually signal losses are very small. And we can understand the reason why. We will understand actually, because we are going to see that in this design the magnetic field produced outside is zero, so therefore this is an indication that this doesn't interact with the outside sources. In any case, we have actually two cables, obviously, for any kind of a cable. There's a cable that carries current in one direction, and there's an outside cable in here that carries the current in the other direction. Right, so I have just shown one example of a coaxial cable in here. I'm going to assume that the central cable is very thin, its thickness is 0. And I'm going to assume that the outer layer in here, this is a conductor as well. This is thick, so therefore it has an inner radius A and outer radius B as shown in here. Right. So in this design, of course, the current is carried, at least the DC current is carried in this direction from the central wire, and in the opposite direction from the outside wire, which is of course in the shape of a cylindrical shell. All right, so a basic problem is to find the magnetic field produced by this design, and as usual, of course, there are actually three regions of interest in here. Is perhaps one of them, the first reason is that region within the cavity, right? There's no cavity actually in the real design. There's just some kind of an insulated material in here, but doesn't matter. We're going to compute the magnetic field there. And then within the conducting shell and the magnetic field outside. So as a result, I'm going to solve the problem, but I'll start drawing the picture again. So the first picture is this. So again, I'm looking at this from the front, so that the current at the center is coming towards us. So that current is coming towards us, and the current at the conductor is going away from us. So that's also I, but that's moving. The current is going into the screen. Right. So as a result, I'm going to look at a point which is let's just forget about these part numbers. Let's just consider a point with a radial distance from the center, which is less than the inner radius of the shell. So as a result, we are talking about a point somewhere in here. So that distance is r. I'm interested in the value of the magnetic field in here. So let me call this as B. And then to find this, we just draw our Amperian loop. So that's in the shape of a circle with radius little r. So we draw it like that. And so then we write down Ampere's law. Let's just first write down the general form. The left-hand side, I don't want to repeat the arguments again, but this is going to end up at the end as B times 2 pi r. And the right-hand side, well, I don't want to repeat the arguments again in here, but you can clearly see that the enclosed surface is crossed only by the central wire, and this thing carries a current I in the forward direction. So therefore, in that case, the magnetic field within that region is mu0 I divided by 2 pi r. Let's just enclose this. Then at the next step, I'm going to look at what happens within the conducting shell. So this time I'm going to draw a bigger picture. So it's the same physical picture, but I'm going to exaggerate things like that. Right. So at this time I have a point in here where that distance is r. So as a result, r is between B and A. Let's remember that. I'm going to raise these because I don't want to make the picture crowded. So the inner radius is A and outer radius is B. Let's just remember this. And the central point is essentially the central wire. All right. So again, I would like to compute the magnetic field there. I don't know the direction perhaps, but that's not that really important. What we are doing is actually computing the components of the magnetic field along this yellow arrow, and as a result, if I find a negative value for that, I'm going to interpret this accordingly as well. In any case, we just choose an Amperian loop as the circle in here. Also, I'm going to choose the direction on the Amperian loop like that. So as a result, we just write down Ampere's law. So that's B dot dl. That's mu0 times I enclosed. The left-hand side is the same again. So that's B times 2 pi r. What about the right-hand side? We can see that the enclosed current is, well, there's a current coming towards us from the central wire. Let me just show it like that. So there's a current in here that's coming towards us from the central wire in here. And then let me show this with a highlighter. There's also a current coming from this this shell-like region in here, which is also enclosed. This is actually a shell too, but it's a shell smaller than the full conducting shell. So there is also a current coming from this region, and no, it's not coming towards us, but it's going into the screen, and I have to count this as a negative because it's basically is flowing in the opposite direction. So I need to count this as negative. I just need to find this magnitude. So as a result, I can see that the current in there is proportional to the area. Yeah, I forgot to mention that of course the current should be somehow distributed uniformly in there. I have to specify this, otherwise the problem is not solvable. In any case, we are assuming that J is uniform there. Let me add this. J is uniform. And so as a result, I can write down the current in there as basically total current multiplied with this area of that shaded region, which is pi times r squared minus a squared, divided by total area of the cylindrical shell. Right, it is that expression actually. Again, let me just repeat what I have said. So if I call this as this shaded area as, let's say, A1, and the total area of the shell, this region in here, as A2. So I'm going to show it like that. So this is A2. So A1 is equal to pi times r squared minus a squared. This is the area which remains inside the enclosed surface enclosed by the Amperian loop. A2 is the total area of the conducting shell. This is basically current multiplied with the ratio of the areas. So current divided by the total area is the current density, and I'm just multiplying the current density with that. All right, so let me then write this thing down on a new page. So therefore here the magnetic field, sorry about this, magnetic field multiplied with 2 pi r is equal to mu0 times I 1 minus r squared minus a squared divided by b squared minus a squared. So you can see that this is b squared minus r squared divided by b squared minus a squared. And so therefore the magnetic field is mu 0 I divided by 2 pi. I'm going to write 1 over r in any case, and then we have a dimensionless factor in here. Again, let me repeat that this is for r is between a and b. Right. Next, what happens in the outside? So again, this is the outer shell, inner conductor, conducting wire. I have a point somewhere in here where that distance is r. I'm curious about the value of the magnetic field there, so I would like to find this. I want to know what it is. So as a result, I choose an Amperian loop that passes from this point. This is my loop. So I immediately use the Ampere's law. So that's the integral of b dot dl is equal to mu 0 times I enclosed. Again, the left hand side is there are many steps. Just remember this. It's b times 2 pi r. And the right hand side is, you can see that in here, there's a current coming towards us from the inner wire. There's a current going into the board from this conducting shell, and that's basically the current I is going inward. So I need to count this, the current on the central wire as a positive I, so as a result I just write this as positive I. I need to count the current that's going into the screen as negative, so therefore this is minus I. And so therefore the right hand side is equal to 0. 0 divided by 2 pi r is 0, so therefore the magnetic field is 0 outside. Let me also write this thing down for radius greater than b. And so therefore first let me just write this thing down mathematically. This is just a summary. So inside, let's say it like this, for r is less than a, we have just the central wire, which is a thin wire. So that's basically the magnetic field produced by a thin wire. So that means that in that region we don't have any effect of the outside conducting shell. So also within the conducting shell we have this expression, which is this is b squared minus r squared divided by b squared minus a squared. So this is for a is less than r less than b, and then 0 outside. So if I draw this as a picture, as a graph, right, that's the magnetic field's component. So inside we have this. All right, there's a linear portion in here, but let's just start with this this region in here. So let me first choose these special lengths in here. So inside, well, within this insulating layer, basically, the magnetic field is proportional to 1 over r. Outside it is equal to 0. And within the conductor somehow it just starts from this value and ends up in there. You can see that the functional dependence on the distance is like the 1 over r something something 1 over r, and then minus something 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 r. So there's a linear part and this 1 over r part. So from here you can kind of say see that this actually is curved down, or it's curving up basically, but it starts from this value and ends up in here. Right? You can easily check that. Apart from the dimensions, you can easily check that the value of the magnetic field at r equals a and at r equals b, you can compute these values by using either of the two alternative expressions. you can see that they match up. So as a result, the magnetic field is a continuous function. So as a result, it has this kind of a behavior. So the significant feature in here is that there is no magnetic field outside. So this is an indication that, let me go back to the original picture. This is an indication that the electrons inside the wires do not interact magnetically with any kind of a magnetic source outside, right? So the electrons cannot apply a magnetic force to a magnet in here. So if I have a magnet in here, then they won't be able to apply a magnetic force. And this implies that it is the vice versa, right? So any magnet in here cannot possibly apply cannot have an effect on the wire as well. In any case, so this is of course only part of the story, because it's not just a DC current in here. So RF wave essentially implies that there's actually current going back and forth. That's basically an AC type of current, and at very high frequencies actually. So as a result, in these cases, of course, there are some other things, some other effects that also appear with the time dependence of the magnetic fields as well. Somehow, with this design, you minimize the interaction of the current flowing on the wire with the outside, outside physical systems. So that doesn't mean that the physical interaction is zero, but it is minimized, and that's why this kind of a design is preferred for these kind of jobs.